All right, welcome everybody. So this week we're going to start off with the goal being to get to SDXL-Turbo, which is stable diffusion. They're really big model, but fast, which is a cool kind of combination. And when Roger and I were preparing to present this, first of all, we noticed that the paper is really, really cool and the contribution's kind of neat. Second thing we noticed was that it uses a lot of the different tools that have come about over the history of image generation. And given that we're kind of at the beginning of the year, we have a lot of new people, some of whom are less familiar with kind of the history. We thought we'd go ahead and do what I'm going to call Jerry, can you enable screen sharing? Sorry. A brief history of image generation. And it's going to bring together a bunch of different streams. I'm going to start off by handing over to Roger, so that he can explain SDXL-Turbo in very, very brief terms. And then from there, we'll go over and talk about the history.
Oh, okay.
Yes, we'll start off with an introduction of SDXL-Turbo, if that's all right.
Unless you know what's going on, that video misses a little. You don't really catch it. That what's happening is that the image generation is so fast that they're actually updating it as you're typing. Anyhow, so you can try it out. There's a pretty limited amount of budget that you get, and the image quality wasn't real high, so you probably have to try out one of the pro, sign up for one of the pro membership or whatever. To get the full effect. Okay, so what we're going to do then is talk about this. The main claim to fame, I think, is just that this is reduced the inference of a diffusion model down to just a very few number of steps. And this is kind of a follow-on, adds to the consistency model stuff that we were studying earlier, where you can see there's a model that is being trained to iterate quickly, and it's being trained by a model that's been pre-trained and has already generated the score function. So what this picture really is summarized the paper we'll be covering, but the key thing to take away is that it involves both GAN style architecture with the discriminator and an adversarial loss, the real fake. It also includes this training of a diffusion model that is a few-step generator, and it involves distillation, which we also had studied early on. So as Selly said, the thought was provide some background to multiple technologies here, provide background so we can all absorb this when we're going through the paper. And Selly, I think that's your lead in then for the historical perspective.
I think that's fair. Yeah, I think so as we kind of look at the again, the reason for wanting to go back and taking a big step back and looking at the history of image generation was that we noticed that SDXL uses these 4 different principles, each of which are a huge contribution to either classification or the various problems that we've had in the deep learning space. And again, what's I think particularly interesting, the way that I kind of summarized with Roger earlier today is that, there are probably, 40 major contributions to machine learning in the last 45 or 50 years. And all but one of them were in the last 7 or 8 years. And so it's a pretty compressed timeline over which all this happens. And so it's just kind of a neat opportunity to go back and look at where did distillation come from? Why is that important? Why does that play a role here? Diffusion, I think we all know a little bit more about, but there's a history there as well. The adversarial discriminator, and then the most tactical thing of all this is that it's called SDXL-Turbo, and it's easy to think that just making something go fast is kind of an ancillary or tactical contribution. But really, as we go back and look at the history of deep learning, performance and cost optimization has actually proven to be one of the most fundamental investments that we've made over the last few years, because it broadens accessibility, it broadens the speed at which we're iterating. It brings more than 5 people to the meetups about this. I mean, it's really, again, it's a great opportunity to kind of take a step back and look at the history. And so at a high level, Roger and I decided to kind of look at 3 parallel histories, and look at, kind of the olden days and where we've come in about the last 8 to 10 years. And just as a kind of a really summary pipeline here, if you look at kind of images and text, let's look 10 years ago at the event horizon. What was the state of the art? We had Google in both of these more traditional kinds of DSP type computer vision, what you'd find in OpenCV, for example, ImageNet, AlexNet, residual networks, vid to vid, and then the convergence with the other ones in GANs, VAE, state models, consistency models, and diffusion models. On the tech side, similarly, Google was really king back then, and the anything other than Google was essentially like bucket of words or hidden Markov models, very, very simple stuff. Then RNNs and deep RNNs emerged, embeddings, which are so cool all by themselves, LSTMs grew, and then the fundamental watershed moment that drove a big chunk of this convergence is the paper called Attention is All You Need. On the generative side, and so again, each of these are individual kind of timelines that have these corresponding milestones that all come together. They're very disparate spheres of work, frankly, but they all come together to create what we're seeing now. Again, at the beginning, pretty rudimentary. These are rule-based expert systems, rule-based learning, HMM, GMMs, as I mentioned. AlphaGo was one of the very first truly self-teaching learning systems, and we can talk about that. Even with its limitations, it was. This is probably one of the big watershed concepts, was that we could learn without teaching. Because up until AlphaGo, and even the first version of AlphaGo, all forms of generative were imitative, meaning that they would model after a human. And then as we know now, as we're kind of progressing further and further down, we're pretty far past imitative generative models. And that, again, all 3 of these come together today. You have to have, in order to do image to text like you saw with SDXL-Turbo, you have to have the ability to analyze text. We're building on top of all of the knowledge that we have about performance and image features, and obviously it's a generative model. And so all of those things kind of converge in today. And so what I wanted to do was take a step back and then just make sure that everyone listening to the paper on SDXL has, I think it's about 5 or 6 key building blocks. And so we're going to go through each of those time periods. And at each of the time periods, we're going to pull out 1 or 2 of the mathematical building blocks and do a deeper dive. Before I move on, any questions or any feedback on the first couple slides here? All right. If you do want to ask questions, there are enough people that you can raise your hand on the whatever reaction thing on Zoom, and we'll make sure to get questions. So with that, I'll stop. I'll take a step to the side, pardon me, and I wanted to comment on some of the variables that we'll see as we go through history. Some of the things that will really fundamentally change again as we move through. I already mentioned cost and time. Again, I think that one's fundamental. It's easy to say that one's not, especially if you happen to work at Google.
Selly,
yeah.
Can I interrupt you? Is your
Please.
mouse moving on its own, or are you doing that?
My mouse is not even on that screen.
That's weird. Okay. Anyway, I have a mouse.
That is weird.
What is that?
You don't see that bouncing around, Selly?
No. It's on. I have 2 monitors. It's on my second monitor. It's over here. My mouse is over here.
Kind of like auto awake mouse movement.
Yeah, it's kind of weird.
Shoot, my boss will know. Okay, let me try putting it all on this screen.
Dad, ask them if they can see it.
Thank you for saying something.
That was too smooth to be human.
All right. Can you see my mouse now on the S?
Yes, I can see it on the S.
Left and right only, up and
Yeah.
down.
Left and right, yes.
Excellent. My mouse has been recaptured. The ghost in the machine has been booted. Thanks, Jerry. Sorry if that was distracting.
Are you
honestly,
still moving the mouse, Silly?
Huh?
Are you still moving the mouse?
Oh no, my mouse was not on the screen anymore. Is it moving again?
Yes.
Oh, there
All
we
of
go.
this high-tech
Well,
AI,
look at that.
ML.
But you
I
can see
think
where
there's
it
a
is.
I think
there's a huge lag because when you said is it going up and down, that up and down happened very late, and that left and right was happening so slow, like a slow motion
Is it
from.
moving
Okay,
now?
it is stopped now.
Okay, so I will leave my mouse on that window and we will retain control of the universe then perhaps. Thank you, Jerry. So again, some of the meta variables that I want you to each kind of latch onto as we go through these different phases, because they each are really important in terms of, again, kind of describing how we've arced through this trajectory to be where we're at today. So data set size, that's another one. One of the things that really early in deep learning, we said, oh, it's because we have so much data. But if you actually look at a lot of the early deep learning stuff, it was on ImageNet, which is 1 million images. We've had 1 million images for a really, 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 really long time. That was not actually the reason for deep learning. But now it really is. The learning approaches. Oh my gosh, we've had so many different approaches. When Roger and I were going through this morning, we talked a little bit about some of the optimization and training, and as we move through architectures, and what was Adam? Adam was the one that jumped out, right, as a back propagation methodology. These were all so powerfully done over the last 10 years that the type of thing that we get to do now is just look at these kind of abstract drawings like this and really understand 90% about what's going on. That by itself, the fact that we can describe an architecture in a drawing like this is truly like standing on the shoulders of giants. And so this work here has been massively impactful. Again, we'll touch on each of these at each of the stages. Training, representation, recall, balance. This basically can be summarized as sometimes we have really, really big models that had lots and lots of parameters and could describe everything, but they were really hard to train because there was too many parameters. Sometimes we had models that were too small and they would overfit. Sometimes we would have models that needed to have structure to them, like pose estimation would be just one thing. And and pose estimation requires defined joints, for example. And so that'd be a model-based learning. And all of those have gone through cycles where sometimes we're using structured, sometimes we're using unstructured or model-free, sometimes we're using large models, sometimes we're using small models. And then in parallel with this, as my good friend, the trillionaire Jensen Huang always says, and you need some more GPUs because I'm out here slinging GPUs if you want some. So in parallel with all of the things we're going to go through, I just want you to kind of think about each of these different things. And if you have questions about what's happening, go for it. So backdrop, before 2012, the kind of the watershed moment for deep learning in my mind is AlexNet winning the ImageNet competition in 2012. There were some CNNs that were around before then. There's a guy named Moez Bakouche that was doing some research and things like that. But really the turning page moment was in 2012 when that happened in the ImageNet competition. Before then, for like 20 years, the cost to contribute to AI was almost $100 million or more. And that's because Google had proven, in the late 90s, that image retrieval could replace just this massive span of everything that we had defined and relied on artificial intelligence doing. That was all based on essentially one major technology, which is the concept of map and reduce, which is that you bring compute power to the storage. You don't bring the data to the compute power, you bring the compute to the storage. And 20 years, that dominated everything, and everything was information retrieval. text lay dormant, right? We had HMMs, bucket of words, tokenization, feature, almost everything that was happening in ML proper was dormant for this entire period. We had, again, in image classification and detection, the state of the art in 2010 was all in OpenCV. It was open sourced, it was fast, it was easy. Har-like features are the ones that I like to harp on because they're so dumb. Har-like features basically describe two dark spots and a light spot, which was the face detector. And it's just looking for your eyes and your nose. That's it. That was like, dun, da, da, da. If you could find two dark spots at about the same Y parameter, and then an X parameter in the middle with a light spot, that was a face. And if you were looking at like security cameras, they had this amazing thing that would look at what's called the aspect ratio of a moving object. And if it was like this and tall, it was a human. And if it was like this and short and fat, it was a car. And that was literally the state of the art for like 20 years. There was continued research in things like different types of regression, linear, logistic, SVMs. But again, for the most part, I think stagnation. And so I think that's where I think this is really an interesting history, because it wasn't like this is a continuation of a long story. It really was pretty discontinuous. I do want to double click on HMMs before I move on, because HMMs have a lot of the features that end up showing up throughout the history of deep learning. I hope most of you guys are familiar with HMMs. If you're not, it stands for Hidden Markov Model. It essentially is a method of processing sequential data using a set of latent variables. So you kind of do some processing on, let's say we're looking at a word and we're looking at each letter. This is the letter A followed by the letter B. And when I see the A, I do some processing on A, and then I store in my latent memory, oh, if it's an A, I think the next letter might be this, or here are the set of words that it might be. And so I'm going to keep that in my latent memory and then move through the processing sequentially each of the subsequent words. For those of, pardon me, for those of you that know where we're going, obviously that has a lot of what we have in RNNs, but I think also interestingly, it tells the story as being the state of the art in 2011 of how kind of rudimentary we were. The latent variables lacked pretty much any sort of structure, the ability to compute and to update HMMs. These were all CPU based in-memory models. So they were very, very highly limited in terms of how could you get complex in terms of even just the representation. Put training aside, your latent variable space was very, very small, certainly not described in the billions, right? As we're dealing with today in our current models. They weren't structured, like I mentioned before. A lot of the neural network research that was being done kind of leading into this and why HMMs were so powerful was that the fully connected neural networks were kind of the rage in the late 90s. And then we went into multi-layer perceptron, and they were very limited, right? Both in terms of the ability to use them for compute and the representational power. And so all of that, again, kind of comes together in the 2012 timeframe when the term deep learning gets coined. Again, ImageNet has been around for about 2 years already, and some of the traditional kind of more traditional SVM and computer vision based algorithms were winning. And then in 2012, AlexNet won, and I believe from that point forward, there weren't even any entries basically for anything other than deep neural networks. Interestingly, though, and again, this is where all those other variables kind of come into play, so much more happened. And this was really when I think we started this meetup in 2015, 2016. And so we had just started seeing some of the standardization of things that were required to be able to broaden this out. Because again, let's remember the 20 years prior to this, all research was really dominated within industrial worlds, at Google, at Yahoo, at Microsoft. What are some of the other companies? Facebook was doing a little bit, but mostly on the storage side, not on the retrieval side. And so for the first time in 20 years, academics have the opportunity to contribute. I mean, like that is just all by itself. you sitting as a master's degree student or a PhD student at Stanford or BU or Vanderbilt, or maybe even somewhere that's not as good like Harvard or something like that, like you could actually buy a GPU, build one of these models, train it, and be at the state of the art. For the first time in 20 years that happened, and you could do it for less than $100,000. Like this was a watershed moment. And so what you're going to see next here is where you see a lot of the standardization. NVIDIA jumped on this in 2014. They had built CUDA quite a ways before this, but they built CUDA-NN. And as you'll see, right, in the battle between NVIDIA and AMD, NVIDIA's winning in software. NVIDIA is winning in software because of this library, not because of CUDA, but because of this library. CUDA and the ability to accelerate math functions has been around for, I want to say like 20 some years. But what CUDA-NN does is it reorders the operations with the knowledge that in a deep learning training pipeline, there are specific operations that you don't need them to be sequential. Maybe they came in this way, but I could reorder them, I could regroup them, I could bundle them, I could use the same memory a few times because memory is one of the big bottlenecks. And that's what CUDA-NN does. It doesn't just accelerate mathematical operations, it reorders them in a way that optimizes for the computational and memory bandwidth limitations of the actual underlying hardware. And so these two result in TensorFlow arriving in 2015. TensorFlow maybe not popular anymore, and everybody's like on Torch, and that's the coolest thing. But TensorFlow is huge because until TensorFlow, anybody know what we were using? Does anybody remember?
NumPy?
Anybody? Come on, someone has to know this one. Ted, do you know this one?
It's written on the
Even
slide,
unmuted,
isn't it?
right when it says name.
It's written on the slide, isn't it?
Oh, is it? Uh-oh, then I cheated myself.
Piano?
Cafe.
Cafe.
There.
It was on a different slide. I thought it wasn't on this one. Oh no, there it is, right there. I chew out myself. Yes, it is written on the slide. It's Cafe. Theano was there too. That's right. Let's not forget Theano. Give it a hug. It was there too, but the dominant research platform was Cafe, and Cafe had this thing called Model Zoo. I don't know if anybody used that, but it would, as cool as it was, Model Zoo meant I could go download this model, which was primarily in like C. I don't even believe there was really any scripting language overlays on it at the time. And so you had to be able to understand C, which meant you had to understand memory, which meant you had to optimize memory, which all by itself like wipes out 50% of your researchers. And then it was pretty archaic. It was operation by operation. You couldn't really work on blocks. And both Theano and TensorFlow introduced the concept. Theano first, by the way, whoever said that was right. Introduced the concept of blockwise computational graphs. And that was, again, just such a huge building block for us to be able to move forward. If you wanted to do a tuning on a Cafe, you had to either literally go in and work at the level of the CUDA call, which included run this operation from this block of memory, move this block of memory over to the card, or you just ran it in the CPU. Those are really kind of your two big choices. And so this allowed the broadening of the research base.
Hey, Selly, I have a question for you.
Go ahead.
So my understanding, AlexNet, that was really the first time that a GPU was used in deep learning, right? That was the introduction.
Yeah.
That was the whole thing. So did Cafe exist prior to that as like, in other words, did all the concepts existed? They just didn't have a GPU accelerator, but Cafe existed as CPU based?
So Cafe, I believe, had just like raw GPU acceleration, but it was more at the level of like, I'm going to build an array, and then I want you to run this GPU op against that array. I'm gonna have you run this mathematical op against this array. So yeah. You had to tune the mathematical operation. You had to tell it, this is going to be a matrix of this particular size. It's going to be shaped like this, versus this in terms of
presumably No autograd or anything like that.
Nothing. Nothing was automatic. It was all every single parameter that you could think of in memory and in mathematical specification had to be spelled out. You also had to manage your workflow. And so it didn't do any of the sequencing or parallelization, even just parallelizing, right? I'm going to run 4 operations against these blocks of memory, move this one, move this one. Just even that basic stuff that was in CUDA wasn't available at that particular time. I did my first AlexNet training, I think in 2013 or 2014, just before CUDA-NN came out. And it was, you missed one parameter of like a vector size or matrix size, pardon me, and your host. And the error messages were straight out of the CUDA library from NVIDIA that were designed for NVIDIA engineers to read their own error message, look it up in their own proprietary book that they didn't give you, and then figure out what the heck went wrong. In fact, I think in 2013 or 2014, there was someone wrote an accelerator library for OpenCV using the CUDA library, and it broke. You could never use it. And so I actually ended up being the one that fixed it, and I made a little branch off of OpenCV, and I was running the de facto OpenCV distribution for a long time.
Cool.
Not on purpose. I found someone else had kind of thought about how to fix it, and I just fixed it, merged it in, and everybody used my branch. So it was hard, I guess is my point. Like the fact that I fixed this one little memory bug meant that everybody could move forward, and until that happened, nobody could move forward, right? Like it literally was kind of that small of a community and that fragile, I guess would be the way I would kind of describe it. And so as 2015 arrived, a lot of people started getting interested in this. You had the first RNNs emerge, and we'll talk about what some of these were and what they did in just a second as we go deeper. For me personally, the moment that it became accessible was when Andre Karpathy started doing his papers at Stanford, his CS231N at Stanford, because he made things so visible. He made the first neural network that you could train on a web browser. I mean, this guy was awesome. So he just left OpenAI, I think, last week, right?
Mm-hmm.
Yeah.
Super sad to see him go, but he was awesome. Somebody asked about scikit-learn. My gosh, I do not know the history of scikit-learn very well. That was around, I believe, around this same time already.
It was existing prior to that time.
Yeah, but I don't believe it was able to contribute much to image at the time.
That's
it was really
true.
more along the traditional kind of linear regression, logistic regression, SVM type stuff.
Scientific computing.
Yeah,
what it was.
I might be incorrect, but I think that was right.
Yeah.
Okay. So with that, I'll kind of jump into a quick double click. I'm going to do a couple double clicks from the background. One was AlphaGo. AlphaGo introduced one of the most interesting concepts that's relevant to SDXL-Turbo, in that it proved the idea of generation, and that the architecture of AlphaGo, essentially the original version, was that had you trained a model on all of the historical games that had been played of Go, and it said this is like the master, and then it would train additional models and then play them against each other to try to kind of get better and incrementally improve. And the concept of self-play, obviously, it incorporates the two primary concepts of a GAN, which is you have one model trying to do something and then another model fighting against it. Now, GANs are slightly different than that, and the way that they did it here obviously is not perfectly to a GAN, but this concept of generating a model to train a model, we'd always, if you read Isaac Asimov, we've thought about this for a long time. But as far as I'm aware, this is the very first time it was used to achieve a state-of-the-art outcome. And obviously, mathematically, winning Go, I believe, if I'm not mistaken, Go has more combinatorial state space than there are particles in the universe, right? And so being able to mathematically converge on that solution was a massive, massive, massive accomplishment. The second thing I'll highlight here, which again, as part of the history of deep learning, is this was highly structured. This one was kind of like a cheat as you go. And I don't like cheating. I don't like feature engineering. But as a stepping stone to get to where we're at, it was a critical one. And so they had things like a ladder. I don't know what a ladder is, to be honest with you, but it's like a specially defined set of parameters. If you have your stones like this and the other players, their stones like this, that's called a ladder. And they literally programmed in ladder, and it was a binary variable, whether there was a ladder available. And that was in the code for AlphaGo. And so it was really structured. The code actually knew about the rules of the game. They trained it on humans. So it was really kind of a bootstrapping would be the way I'd kind of look at AlphaGo. But in the process of building that bootstrapping, they made the watershed discovery. The other thing that I would double click on here is RNNs. And so as I mentioned here, RNNs emerged in 2015, really kind of doing the Wikipedia training set, which people were downloading the Wikipedia training set, training it, and then using it as an autoencoder. Can I recreate Wikipedia using noise fed into an RNN? And so RNNs, what was it, Roger? You said there was something from like the 50s. I forget what it was. Did you get the name of that?
Yeah, just that it was hard for us to find kind of the source for RNN in a machine learning context, because it goes back, the concepts 50s. I think there was even some mention of something like that in 24 or something like that. So, yeah.
But again, in about 2015, with these three things coming together, AlexNet, cuDNN, and TensorFlow, there was an explosion in papers reopening this idea of using this recurrent structure that is present in an HMM, but applying it in a deep neural network. And so we'll watch a quick video on that, if that's okay. So I'll unless there are questions, are there any questions at this point? Otherwise, we can watch a quick video on RNNs. Bada boom. Bada boom.
Dear fellow scholars, this is 2-minute papers with Károly Zsolnai Fehér. Artificial neural networks are very useful tools that are able to learn and recognize objects on images, or learn the style of Van Gogh and paint new pictures in his style. Today, we're going to talk about recurrent neural networks. So what does the recurrent part mean? With an artificial neural network, we usually have a one-to-one relation between the input and the output. This means that one image comes in and one classification result comes out, whether the image depicts a human face or a train. With recurrent neural networks, we can have a one-to-many relation between the input and the output. The input would still be an image, but the output would not be a word, but a sequence of words, a sentence that describes what we see on the image. For a many-to-one relation, a good example is sentiment analysis. This means that a sequence of inputs, for instance a sentence, is classified as either negative or positive. This is very useful for processing movie reviews, where we'd like to know whether the user liked or hated the movie without reading pages and pages of discussion. And finally, recurrent neural networks can also deal with many-to-many relations, translating an input sequence into an output sequence. Examples of this can be machine translations that take an input sentence and translate it to an output sentence in a different language. For another example of a many-to-many relation, let's see what the algorithm learned after reading Tolstoy's War and Peace novel by asking it to write exactly in that style. It should be noted that generating a new novel happens letter by letter, so the algorithm is not allowed to memorize words. Let's look at the results at different stages of the training process. The initial results are, well, gibberish. But the algorithm seems to recognize immediately that words are basically a big bunch of letters that are separated by spaces. If we wait a bit more, we see that it starts to get a very rudimentary understanding of structures. For instance, a quotation mark that you have opened must be closed, and a sentence can be closed by a period, and it is followed by an uppercase letter. Later, it starts to learn shorter and more common words, such as fall, that, the, for, me. If we wait for longer, we see that it already gets a grasp of longer words, and smaller parts of sentences actually start to make sense. Here's a piece of Shakespeare that was written by the algorithm after reading all of his works. You see names that make sense and you really have to check the text thoroughly to conclude that it's indeed not the real deal. It can also try to write math papers. I had to look for quite a bit until I realized that something is fishy here. It is not unreasonable to think that it can very easily deceive a non-expert reader. Can you believe this? This is insanity. It is also capable of learning the source code of the Linux operating system and generate new code that looks quite sensible. It can also try to continue the song Let It Go from the famous Disney movie Frozen. So, recurrent neural networks are amazing tools that open up completely new horizons for solving problems where either the inputs or the outputs are not one thing, but a sequence of things. And now, signing off with a piece of recurrent neural network wisdom. Well, your wit is in the care of side and death. Bear this in mind wherever you go. Thanks for watching, and I'll see you next time.
So can we do that again, Roger? You promised to sing, and you did. I didn't hear you singing.
It is also capable of learning the
Where
the
we go.
song
Go
Let
ahead.
It Go
No.
from the famous Disney.
So some cool things that you're going to see there, right? You know, the ideas of the things that we're seeing right now with ChatGPT around source code, around writing essays for our high school students so they don't have to do them. These were all ideas that were as recently as the first rendition of Frozen, you know, still becoming possible, but not yet possible, and now very, 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 very real.
What year was
And
that?
so I wanted to spend 10 seconds on RNNs before we move on to the next topic. Any questions about RNNs before we move on?
So the RNNs can be traced back to something called Hopfield networks in 1982, I think. So
Thank
they have
you.
some
Is that
energy
Sachin?
and- yeah, Sachin.
Yeah. That was what Roger and I were trying to read about this afternoon. I don't know much about Hopfield networks at all. Does anybody know more that they could share in terms of the history?
I don't know much about the history. Yeah, go ahead, Sachin, please.
Yeah, so I think what happened is Hinton took some hints from Hopfield networks and proposed the first one around 1986. And I think then it kind of took a low thing after 1986. There was not much work done over there. So he tried to access the pattern, whereas the Hopfield networks, I think, work in terms of energy activations. So it's slightly different, but those were where the state is stored. So.
Do you have a definition for a Hopfield network?
Give me some time and I'll dig it up. So I'll share later on. So
I think the point, though, Sachin, that you're making is really good, though, is that the last 8 years are really kind of like, we have a lot of these ingredients kind of coming together, and then critical heat gets achieved. And all these, even ingredients that we didn't quite expect, are coming together in ways that we didn't expect. And it's just kind of building on itself and exploding. And so
that's common.
Some of which have been lying dormant for years and years.
Yeah, that's common in science and engineering, right? You know, somebody comes up with something and it looks interesting, you go in this tangent and it doesn't go anywhere. And then somebody else has another problem and applies it to that, and boom, there you go.
Yep.
Yeah.
I think, again, though, just what we're seeing specifically inside of deep learning was just the speed and the number of things that are converging is pretty mind-blowing. So unless there are other questions, I will.
So the other thing was the 2012 AlexNet, they went from 60,000 to, I think, 60 million parameters. That was the first time. That was a huge jump. And he was forced to take the GPUs at that point. And there also Hinton was part of the thing. So.
Yeah. And I was going to go, if we look kind of further here, that trend only continues, right? Now we're using boards that start with B's to describe parameters. And that really was the first time that it was actually worthwhile, frankly, re-looking at a lot of these different problems. And so the number of parameters and the ability to make use of those parameters, we had built really complex, fully connected, they weren't feed forward, they were associative neural networks in the 90s. and then you'd stick them in a supercomputer and just say, go chew on this for a while and see what happens. But they just didn't converge. They didn't, come out with anything interesting. And so it's really a combination of the structures that we're using, the architectures, the training methodologies, the advancements we've made in backpropagation that all kind of come together to make these things possible. Next slide.
Dear fellow scholars,
Sorry. Next up will be structure. So talking about not just kind of the overall shape of the way that data flow through our model, but actually starting.
Selly, I think
Yes.
there was a question in the chat.
Oh, sorry. Thank you. Someone's giving away GPUs. Is that the question?
No, I thought somebody had a question. Did I hear Dave correctly? Oh, Dave is giving away GPUs. Oh, are you giving away GPUs, Selly? No.
No.
You get a
really
GPU and you get.
I can see if I can help you, and as Jerry said, my friend Oprah might be able to help you too.
Yeah.
So as we transition from kind of the way that the model exists within its data, this is kind of the way that the model is here, and the data flow through it in an RNN, something like this, or flow through it like this. With a CNN, what we're actually doing is we're restricting the way that the nodes of a network can communicate with each other mathematically, and we're restricting some of those in order to say, I don't want every edge. Sorry, I don't want to have an edge between every single point in my network, because that becomes mathematically intractable. I want to really, really just look at the things that are near to me. And again, this is not something new, but the concept of a kernel has been around for a long time in images, right? The most simple of these was the Gaussian kernel that you would use in Adobe Photoshop to do a blur, right? And that was just a very, very simple Gaussian kernel. And so the concept here is to take those kernels and then use them to restrict the edges in a network to make them mathematically tractable. So with that, I will allow our teacher to give us, I think, about 5 minutes on CNNs.
Welcome to our Pangupta channel. If you have still not subscribed the
I
channel,
have to apologize first for this one. Roger's laughing, sorry. So the content of this video is on point. And yes, Richard, I have to apologize. If we had another hour or two, Roger and I would have done voice to text and then text to speech and put a better voice over the top of this. We did not have the extra time. I did not write down the entire transcript, so I can't do it. I'm actually a little sick, so that would even be bad. The voice is jarring, and so I apologize. The content is on point, though. And so we watched a bunch of different videos, and we didn't find any that were nearly as good in terms of content in 5 minutes as this one. So just brace yourself.
then subscribe it and do not forget to press bell button to get future videos notifications. What is convolutional neural network? Convolutional neural network is one of the kind of neural network architectures. Its architecture is different than feed-forward neural network. This architecture mimics the connections of neurons in the human brain. This network takes an input image and assign weights to feature in the image to output the predictions. The usefulness of CNN lies in the ability to learn features from the images automatically without taking help of hand-engineered features. So basically, broadly speaking, we have input layer, then set of middle layers, and then output layer. Input layer takes input image. Set of middle layer have layers of features extracted from the images, and output layer is the predicted layer. How CNN is better than feed-forward neural network for image classification or images in general. The images has pixels in it. The pixels are not independent of each other. Any object detail present in the images is collection of pixels. So pixels in images has spatial dependencies which can only be done by CNN architecture. We will see how computational power is saved through CNN for images. An RGB image has 3 images, red, green, and blue, which are also called channels. Consider a 216 by 216 RGB images. It has total of 216 multiplied by 216 multiplied by 3, which is equal to 139,968 pixels. With simple feed-forward neural network, it will be very difficult to process so many features at a time due to lack of computational power. So here comes CNN, which will reduce the images into forms which will be easier to model to get final predictions. Basically, CNN removes the noise from the data and thus reduce the data size. Terminology in CNN. The important terms in CNN are convolutional layer, pooling layer, fully connected layer. In relation to convolution layer, there are more terms like filter, filter size, padding, stride. We will talk about each now. Important layers in CNN architectures. The middle set of layers are mostly either convolutional layer or pooling layer. What is convolutional layer? RGB image is read as a 3D matrix, height by width by depth. The convolutional layer makes use of a set of learnable filters. A filter is used to detect the presence of specific features or patterns present in the input image. How does convolution layer helps? Convolution is done to extract the high-level features such as edges and curvatures from the input image. The first layers in set of middle layers involves convolutional layer, which helps in capturing the low-level features such as edges and color, etc. Subsequent layers in the set of middle layers captures high-level features, which gives broader understanding of objects in the images. What is filter or kernel in convolutional layer? Kernel or filter is shown in the middle. Basically, it is a matrix which moves over the input image as shown in left. Each element in the kernel multiply with corresponding element in original image at any instant and then adds all these value to get values like 114,328 minus 26 as shown in right. The filter moves to the right with a certain stride value till it passes the complete width until the entire image is traversed. What is convolved feature map or activation map? The output image after the filter has moved across the input image is called convolved feature, then convolved feature is passed through some activation function like than, sigmoid, relu, etc. Basically, activation function is used to help in deciding if the neuron would fire or not. That means if the neuron will output anything or not in the current layer. What is stride? Basically, in this image, filter is taking one step equivalent to 1 pixel. So it is stride 1 movement. Stride 2 will be something like this, where at each step is 2 pixel shifting.
So I'll pause right there. I think we've got the major concepts out that I wanted to get with convolution, and my arch eye texture doesn't want us to continue anymore. It's just jarring. There's 3 things that I would highlight here that she touches on, or he touches on, that I think are really important. The first one being that in AlexNet, for those of you that don't recall this diagram isn't just an average CNN. This is actually, like, I'm 90% sure this is actually AlexNet, because you had to get these exact widths and depths of these intermediary layers perfect. Otherwise it didn't work. Like, it fell down. And these were the hyperparameters of the model. Was it, and she mentioned stride and the width of the convolutions and how many you have at each of the different layers. And if you got any of those things wrong, you were host. So adding more computational power didn't really help. Again, mind-blowing accomplishment. Let's just pause there, right? Like, still mind-blowing, but it was very fragile. And so from a model perspective, you had to really tune each of these different things in terms of the hyperparameters. The second thing that she mentioned, which I think is the real key contribution here, is she doesn't do the math for you here. She should, but it's like that by not doing, CNNs are not about doing the right thing. They're about not doing a bunch of the wrong thing. That if you were to just use the fully connected layer, you'd have to have all the pixels and all of the different channels connected to all of the other pixels and all of the other channels for every feature that you want to detect. That's not just once. I believe AlexNet had like 256 features at one layer that it was using for the filters. So you may have to do that not only 216 times 216 times 3 times 216 times 216 times 3 times 256. And just, it became an intractable amount of math for 2 reasons. One, it's just a lot of math, but you could do that. Like, there's computers, you'd push go, maybe you go get a cup of coffee and come back. The bigger problem was that they didn't converge because so many of those values weren't important. Even if you did compute them and then you computed them again and computed them again, they were never important in the first place. The relationship between this pixel up here and the pixel in the upper right and pixel in the bottom left is so minuscule that to compute that would be in the case of CNNs, a mistake. And so that's how we moved forward. We used this concept, the knowledge that we had as the observers, to force a structure on a model in order to reduce the computational complexity. As you'll see, and as we proceed, we want to start removing those things, right? So that's a very not specific model. And so over the next few years, what we're going to talk about is how to actually remove some of those limitations that we structurally impose in order to make increasingly general models.
And welcome to our Pan-Gupta.
You're done. Okay,
Kelly?
go ahead.
Yeah, actually, that was a point that you were making earlier about AlphaGo, was that their initial approach, and it was breakthrough, had a lot of structure kind of hard baked into it. It was the feature engineering was done, added beforehand, and then it was trained on human historical challenges. But they later released Alpha Zero, I think was the final release, that basically had no prior knowledge, no feature engineering, and they just did the game theory playing against each other and achieved superior results over time.
That's right, and they'd actually tried doing that when making AlphaGo the very first one, but they found that it wouldn't converge because they only had a limited number of models. They were just learning how to do this for the first time. And so actually, if you look at the AlphaGo, the original AlphaGo paper, the current model would always play against a model from a couple of generations ago. And that was to keep them disparate in terms of their play style, so they didn't just cycle on themselves. And I remember there's a specific set of terms and tests that they use to kind of determine that. But Roger, you're on point here, which is that, so this kind of brings us to 2015, 2016. The next 3 to 5 years are amazing. Don't get me wrong, but really kind of focus on, okay, now we just reached this new plateau. We need to build an entirely new toolkit of what do we do once we're here? How do we think about all the complexity of these compute? The nonlinearities were like in the one that we were just looking at with a LSTM is a tan H. A tan H function is not very fun for a computer to compute, especially if it has to do it millions or billions or trillions of times. A tan H is super duper duper not fun. It also has, some other properties in terms of its shape that make problems. Even like a sinusoidal curve or a cosine curve. All of the nonlinearities that we used until about 2016 were super smooth and a pain in the ass to compute. And so we started looking at things like ReLU, which is just 1 or 0, right? And it's easy to compute the derivative of that too, right? There's all kinds of things that you can do here. We started doing discretization because the hardware was reaching its limits. We were using floating point 32s to compute everything. And then we did some experiments. Oh my gosh, if we do floating point 16s, we get almost the same results and we save 50% of the computation. Vida, you've got a question. Vida?
Vida, you're on mute, perhaps.
Yeah, sorry. Hi. Wanted to add that the reason like sigmoid and tangent hyperbolic and things like that weren't working good enough wasn't the computational aspect of it, although you're right that they are complex, but it was the vanishing and exploding gradients that they have these saturation points. It wasn't quite ReLU does better.
They were used by default though, kind of just, when we were sitting as scientists in the 90s thinking about how to create a nonlinearity, let's just use sine, right? And so this was the first time we really did aggressive practical research to say, hey, they also have this problem of they explode, right? And so we had multiple types of ReLU. We had leaky ReLU. We had there was a bounded version of ReLU that went from 0 to 1. So there were a lot of different ways to kind of look at nonlinearities. And this was the first time we had a sufficiently large corpus of work to be able to actually perform a lot of that analysis. But you're spot on, right? Like there were all kinds of things we had to solve here. What comes out the other side, though, and what I'm kind of trying to show here is that we come out with this new set of building blocks, this new toolkit that allow us to look at a paper, to look at an architecture, and to, in a very dense manner, using shared terminology, shared toolkit, and the ability to take that and reduce it to practice very, very quickly, a shared set of understanding about what we're doing, why we're doing it, at a very high level of abstraction. And I don't know how much you guys want to spend on each of these rows, but I thought I'd spend at least like kind of 10 seconds just to touch on them, because these are here because they're each really, really big contributions. And without them, we would not be able to do things like, again, going back to that diagram. This is I think this is a transformer, isn't it? Isn't that what this is? But the ability to kind of look at something and say, oh, here's what this does. You go back to AlexNet, and that diagram that I showed on this video, people were just looking at that for, I want to say like 2 years, and just, oh my God, could we do this? And it was so hard. It was so hard. When the original AlexNet,
welcome to our pan.
No. When the original AlexNet came out, in order to implement that, as I mentioned, you were going through and manually stating this vector is this size. I'm going to execute this convolution of this exact size using this exact stride. But you couldn't even do that. You had to implement stride, which was a for loop, right? And instead of stepping by 1, it was a for loop that incremented by 2 or incremented by 3. If you attended the very first workshops here, that's what we did. We actually implemented these for loops that all ultimately, again, became kind of Theano and TensorFlow, so you didn't have to do that. ResNet was another big one that came about. ResNet took the ideas of AlexNet and basically said, we can use this thing called a residual edge to basically say, if I just add more compute and more compute time, I can keep training this forever. And this is actually what brought Microsoft back from, I wouldn't say death, but like pretty close to death as it relates to AI research. I mean, they had contributed nothing for dozens of years at this point. Microsoft research was destitute, and they found this way to use a residual edge to just say, okay, I can use this block, and then I could do 2, and then I could do 4, and then I could do 16, and then I could do 32, and then I could do 64. But what that did, unfortunately, was it pushed us to the point that nobody could contribute anymore because the cost to train that was really high. And then emerged distillation. And the reason I spend a bunch of time on this is that if you're paying attention to the first bit, distillation is one of the fundamental building blocks going into SDXL-Turbo. And we'll spend a couple minutes on that. I think that'll probably be the last video we watch, actually. It's probably distillation today. Keras was the extrapolation of Theano and TensorFlow. Just take these things and you can create an entire model architecture in like 20 lines of Python. It was super descriptive. It captured everything we needed to have. Things like stride, the for loop of going up and down across a block of an image. No, I'm just going to call that a convolutional layer. I'm not going to make you do the for loop. I'm not going to make you define stride. And that was really, really dope. The nonlinearities I already talked about. Atom, my gosh, right? I'd forgotten all about this until Roger and I were bantering this afternoon. There was a ton of work that needed to be done on how do you do backprop? How do you actually propagate loss back up through a network? Do you do big steps? Do you do small steps? How do you deal with local minima and local maxima? Because that was just a massive problem. Every time you retrained, I did my first retraining of AlexNet, I think in 2015 or 2016, and I chose the wrong parameters for my learning curve, and I got stuck in a local minimum that sucked, and I could never get out of it. And I'd already spent like 40 hours of compute time on it, so I was really stuck. And so these were things where Atom modulates the step size of your back propagation based on your loss and the maturity of your search. And for the most part now, these algorithms are just built into our toolkit. You don't even really have to know about them. You're going to probably be 90% right just as a function of like doing whatever's in the paper. Jupyter Cloud Computer, for the first year and a half running this meetup, every single time we had a meetup, we would have somebody show up and they'd bring their laptop and they say, I tried to install CUDA NN and I couldn't get it to work. Can you help me? And that every single week. And so we would have working sessions where we had to teach people how to set up their laptops. We had people that would share their laptops. We had some that were pre-configured, and now we have Jupyter notebooks. These are each massive leaps of technology enabling access and speed and training. The discretization of the TPUs. I mentioned the the floating point. We go in and out of model-based learning, right? So pose estimation, my favorite model-based structure, capsule networks. Anybody know what capsule networks are? Anyone remember?
It was brief.
Vida, go for it.
Conceptually, I kind of know what was going on. So it was like having to do with objects and their poses, and then if there were multiple, like things that were saying the pose must be this, and they agreed, then the pose was that, and that kind of thing.
That's right.
Yeah, kind of like
if we agree, which is the right terminology. Go ahead, Ted. You're gonna say something?
Yeah, so kind of like you have like sort of your arm subnetwork and your like torso subnetwork or something, right?
Yeah, it was described as reverse graphics.
Yes.
Right. And it was basically that you were trying to define an object and then define the transpose that it had undergone so that your view of it resulted in this particular projection. And so you're trying to reverse determine what is the object and what is its pose or transformation that it's undergone so that I'm seeing these particular pixels. It was the first network that had 1.5 trillion parameters that were not used, none of which were useful. And it only solved one problem, which was, I think, MNIST, right? And even that only briefly.
It was a good concept. It was just very difficult to.
Yeah. But it was a neat idea. And this is, again, one of those stepping stones that's needed is we did a lot of different model-based things. Pose estimation remains a good one. But we did pose estimation for like human generation for a long time, right? So a lot of images of humans were based on poses, which would obviously maybe solve part of the hallucination problem that we currently have, but like, let's just move on from there. So then we had a lot of finicky models where if you were to look at, I think it was Roger, you presented a paper about 3 years ago where we were looking at the hyperplane of loss in a local area. And there were certain models where the local minimum was very, very sharp, meaning that if you perturbed just a little tiny bit, your model went from being state of the art to being the worst thing anyone's ever come up with, and it's worse than noise.
Yep.
And then they started to figure out, how do we flatten out the areas that we're looking for? How do we make sure that the model that we're generating doesn't have these really sharp hyper edges in the hyperplanes or in the manifolds that describe the loss landscape?
Yeah, it was visualizing the lost landscape.
Visualizing the lost landscape.
Yeah. And it was really interesting to see how the lost landscape changed, like with a residual net versus just a deep network, if you recall. It had that flattening effect, made it much smoother, much easier to train.
And as you might imagine, right, a network that has a flatter kind of optimal space or global minimum or even a local minimum means that more people can use it, right? You or I could go download the model, and if we mess up just a little tiny bit, it's robust to all those different perturbations. And again, I'm not going to go into the detail during this period, but all of those things moved. And the way that I would kind of summarize the way that we come out of that into today is that we can operate by looking instead of at all of these details, right? TensorFlow and Theano got us out of looking at memory, thank God. And then these things got us out of looking at individual layers of networks and looking at network blocks, looking at theory. And the way I would kind of describe the history of theory was that for the first 5 years of deep learning, theory followed practical experiments. Did we really know why AlexNet's hyperparameter of 45 and then 256 worked? No, but we started performing analysis and we started kind of coming up with some hypotheses about how to think about these things. And we started developing theories. We started developing, maybe at times, I think early, too far, we tried to kind of reduce these things to mathematical equations that we were already familiar with. But now, as again, we get to kind of the 2022 timeline, we start entering a phase where theory can start driving, where we can start running our experiments based on the results that a theory would predict, instead of writing a theory to describe why this happened last year. And that's also a really, really neat transformation that's, I mean, literally maybe 3 years old at this point, maybe 4. Any other questions as we kind of move on from this phase of deep learning, which is, I think it was really, really fun, and I'm super glad to not be doing this part anymore. That would be the kind of way I would describe it. Like super intellectually engaging, so much stuff. Any other questions? Otherwise, I will move. Okay, cool. This, I think, will probably be our last video of the day because I'm losing my voice. And it's a cool one, and it's the right one for us to use to kind of pick up next week, is going to be on distillation. All righty.
Ciao a tutti, and welcome to this new quick episode of SVN channel. Today, I want to talk about knowledge distillation, a methodology that is part of all those optimization techniques that let us unchain models from the cloud and deploy them directly on board the machines. We have pruning, quantization, weight clustering, and many others. However, knowledge distillation is radically different from all these ones. The main idea is to train a big model or an ensemble of models and then squeeze their knowledge into a small one. It was first proposed by this paper, but then it became famous thanks to the one and only Geoffrey Hinton. He presented this idea in this paper, Distilling Knowledge in Neural Networks. It starts in the introduction talking about insects and their larval form. Hinton. But then he proceeds giving an important tip about knowledge. The question is, where's knowledge in a neural network? You could think inside weights, but looking only under this light, it would be very difficult to see how to compress a network into a small one. Instead, Hinton suggests for this problem to look at a network as a function that transforms input in output vectors. So, for instance, in an image classification task, we have an image that is transformed in a probability distribution, usually with a softmax operation. And here's the trick. In contrast to labels, with a neural network I have information of all answers, also the wrong ones. And if you think about it, that's really helpful. I have practically a concrete mechanism to probe how a network is generalizing. Indeed, if, for example, I have a large model, very good at classifying digits, that model with its predictions is implicitly saying me that a 9 is more similar to an 8 or 3 than a 1. And that is simply watching at its output. But in practice, how could we do? There are two ways. The region 1 proposed by Hinton, soft distillation, and hard distillation, proposed by this guy to train a vision transformer. With the first one, we simply select a way to measure distance between two distributions, like the KL divergence, and then we add it to your loss function. So we have a weighted sum with, for example, process entropy and a KL distance between the softmax output of the cumbersome model, usually called the teacher, and the softmax output of the small model, also known as the student. As you can see, there's a T, and that's the temperature parameter. Normally T is set to 1, but with distillation we set this parameter to a value greater than 1, obtaining a softer probability distribution. So, increasing T is possible to circumvent the small probability value of negative answers. And that's it! With this loss, we cannot train our small network. Instead, our distillation is even simpler. We take the argmax of the softmax output of the teacher and we perform a weighted sum with yaw loss and true labels and a cross entropy loss between the student outputs and these new labels computed with the teacher. It doesn't seem so clever, but it's especially useful if the student has an input slightly different from the teacher. And that's all for knowledge distillation. As always, I leave you in the description a notebook where you can play with knowledge distillation and yeah, have a nice day. Thank you for watching.
Cool. There's a question in here that I don't know the answer to. Mahmoud asks, the distillation technique used in a consistency model, are those different or the same than this one? Dev, maybe, or does anybody feel like they want to raise their hand and try that one?
I just typed an answer.
Yeah, okay.
Oh. Mahmoud, does that make sense?
Can you repeat again?
Ted, do you want to try?
Yeah, so fundamentally the Hinton paper, what you're doing is you're saying, I'm going to use the teacher to provide better answers. Okay. So my labels. So normally when you train, like back in those days, ImageNet, MNIST, right? You say, here's an image, I'm going to give you a label, this is a dog. And you train it from scratch. But when you do distillation, what Hinton said is, don't give it that, actually give it, I'm 94% sure it's a dog. 3% think it's a cat, 1% think it's a fox. And that's actually more information than if you just say it's a dog. And so then the student learns a lot faster and it's learning a lot of other information. So what the video said is, for example, an 8, you'll see often over and over and over again, the probability of an 8 is a lot closer to the probability of a 3 because those things look similar. And so that pattern implicitly, the student kind of figures that out. Okay. So you ask, is it different in the consistency paper? And it is, because rather than giving you better answers in that particular technique, the teacher is used to pick good training examples. So which 2 adjacent noised images should I train you on? And when they don't have the distillation technique, they just randomly add Gaussian noise and they train on it. But it turns out that's not as good because the random noise isn't necessarily on that ordinary differential equation that they're trying to learn. So it's approximating it, but it's not exactly. But when you use a pre-trained diffusion model, you get much more accurately 2 nearby images that are on the same ordinary differential equation path.
Thank you. I got it.
Yeah, but at the end of the day, even if you don't understand the ODE stuff, it's about, do you use it to pick training examples or do you just use it to
the model directly?
Did they, in the consistency model, did they actually use the term distillation or did they just use the term teacher?
Actually, there are 2 techniques. One of them is isolation. There's no teacher training model in isolation mode, and then other technique is distillation.
Okay.
Yeah, he does actually use the word distillation, and it's a fair use. It's just a slightly, the teacher's picking slightly different things. They're picking examples instead of picking labels to show the student.
Right.
Okay, thank you.
There's a second question in here from Richard, which is, are we using the same data to train the distilled samples, or are we using supplemented data? Does anybody want to take a stab at answering that one?
My understanding is it's the same data or a subset thereof. It doesn't require as much data to train. I think they train more quickly, but I think it's the same data set.
Yep. Anybody else want to add anything to that? Yeah, so again, what they do is if they're looking at, let's say, this digit, the number 9, in order to capture this softmax, which is what they use to train, they use the same exact training data, but instead of training it on the one hot, which would be that this is a 9, you're training it to try to recreate either this, the final layer, or another intermediary layer. So you're basically, instead of trying to predict, is this a 9, you're trying to predict this PDF. Or you could even go further back and say, instead of trying to predict, is this a 9, I want to understand that what the teacher thinks. If I were to go back to this layer here, the second to last, what are the features? I don't even want to have a summary of the PDF. I actually want to be able to learn the features from this prior network. And so David's question, is this trying to copy the original network with less layers and higher density? Yes, that's exactly what it's doing. Is that you're trying to, typically the teacher model would be very large and complex, and thereby able to generate really high quality features, or again, really high quality final PDFs. However, by training a smaller network to get a higher fidelity against a higher fidelity output, meaning that instead of throwing away this PDF and saying this is just a 9, you use this PDF as your Y. This is your target variable for the new network. You're able to capture and extract a lot more information between here and here using this as your target Y. Okie dokies. And in general, results in faster and much smaller networks. With that, I think we're coming up on time. I will give a hat tip to my friend Dave, because this is the next slide here, and I still remember the day that David Hani showed up, and he said, "Hey, I want to do a presentation. I want to present on this thing called, I know that we've been mostly doing images, but I want to talk about text. And there's this rad thing called attention is all you need." And I was like, what a distraction. When we get back to videos, this isn't going to be useful. It's not going to be interesting. And who are you anyway? And this was like the best paper presentation ever. It was so good. So we'll use this as the pickup for next week, because this is, again, distillation transformers. These are all the big building blocks that go into SDXL-Turbo and all of the generative models that we're using today. Before I wrap, any final questions from anybody?
So,
okay. Thank you guys all. I will hopefully see you next week. And if you haven't sent your messages in the chat to join the Slack and you still want to do that, go ahead and do that.
A quick one, in the CNN, when you look at the filters and in the attention in case of transformers, are those kind of ideas that they later on built same for the transformers? Is that a fair assumption?
I didn't 100% follow the question.
When you looked at the CNNs, right, what we look at is that we are able to get features as we look at the spatial relation amongst the things, and that's kind of a limited attention, right? Whereas the transformers takes the attention much longer across the entire sequence length. Is that something that they were working on? Is that the right intuition?
That is, at least as far as I'm concerned. Does anybody have anything they want to add to that one?
I think go ahead, Ted.
No, you should go.
You go ahead, Ted. I was driving, so it's kind of hard to go back and forth.
So I will say that yeah, at the crux of it, you want to know what other things you should pay attention to and do computation on in order to calculate some feature that you're interested in, right? And so you could say that at the crux of it, that's what attentions are always doing. But it's very, very hard to interpret what exact patterns are they really figuring out. And I could say more about that. But so like you're absolutely right in terms of foundationally, that's why they call it attention, is because it's trying to say, I'm going to, again, put some weight on inputs from certain places and kind of ignore the rest of the world. But then it gets really hairy in terms of like, yeah, what exactly are you calculating? It's not as simple as like a vertical line detector anymore.
Yeah, because CNNs also are inherently hierarchical, and things like that. So they're like Ted said, kind of trying to accomplish a similar thing, but they are very fundamentally different mechanisms. The CNNs are also hard limits, right? So if you have a 3x3, you're really only looking at this 3x3. Attention tends to be, big long PDF of stuff, right? So it's a little bit, again, same kinds of ideas, but a little different.
Yeah, I'm actually really interested in research on how this stuff works. So there's a subfield called mechanistic interpretability, where you sort of try and break it down into smaller parts and into little circuits and things like that. And so the latest research there is that you can think of a CNN as like there's vertical lines, there's diagonal lines, there's colors, there's textures, these kinds of things. It's easier to figure that out because the number of features that we're trying to extract from an image is approximately equal to the number of parameters, the number of filters that we have in our CNN. But what people are finding is in language models, the number of features we have is maybe like an order of magnitude larger than the size of our models, which means that, to use the fancy term that people are using, a particular attention pattern or whatever will be polysemantic. It's actually taking sparse signals and it's compressing multiple of them into one place. And so that would be the equivalent in a CNN would be like, this thing is 50% a vertical line detector, but it also gets used for detecting very rare frog skin textures. And because they're rare, they're sort of mutually exclusive.
That the sets are essentially mutually exclusive, and so then you could combine them in a way that you could still discern.
But you need to see the master scheme to know that like these three things will only combine if it's a frog. Otherwise, those same exact components will combine differently to tell you that this is a daisy. And that makes it much, much harder to interpret these days.
Cool. Well, guys, thank you. Please join us next week. If you don't have the opportunity to stick your message in here, the organizers on the meetup site can also get you added to the Slack, so you can message us there. All right, guys, thank you very much. See you next week.
Thanks, Sally. This was awesome.
Thank you.
Good job.
Thank
Take
you.
care,
See
guys.
you next week.